Morning, everyone, honorable session chairs, distinguished reviewers, and fellow researchers. Today, I am honored to present our research paper titled Enhancing IDS Robustness Through Adaptive Statistical Feature Selection with Needle-Driven Thresholding. This work was conducted by myself, Marissa Angelina Santoso, along with Matthew Lim, Nicholas Kenny Hendrawan, Satriadi Putra Santika, and Hidayaturrahman from the Computer Science Department, School of Computer Science at Bina Nusantara University. So, let's begin with some background. IoT ecosystems are growing fast, but that growth introduces critical security weaknesses, particularly because these devices are limited in memory, power, and also processing capability. The conventional rule-based IDS relies on fixed patterns, which means they fail against evolving zero-day threats, and the stakes are real. Global data breach costs reached an average of 4.88 million US dollars in 2024. On the other hand, the advanced deep learning and also complex machine learning architectures can achieve high accuracy, but their high computational load hinders resource-constrained IoT devices. So, feature selection is essential. It reduces the processing overhead, retains only the most critical attributes, and also enables efficient edge deployment. So, this leads us to three concrete problems. The first one is the curse of dimensionality. High dimensional network telemetry leads to computational bottlenecks, latency spikes, and also high false positive rates. And the second one is the limitation of traditional filters. The standard statistical filters like chi-square, ANOVA, and Pearson relies on hard-coded top K rules or manually set thresholds that cannot adapt. And the third one is the generalization failure. A fixed feature count for optimized for one network topology fails to generalize across another. So, to address this, our research outlines three objectives. The first one is to build an end-to-end pipeline that adaptively determines the best subset of security feature without requiring the manual top K parameter tuning. And the second one is dynamically identifying the mathematical elbow point on feature importance ranking curves using the needle algorithm. And the third one is improving model robustness by drastically reducing performance variance across highly differing network topologies and also attack models. So, here is our proposed research pipeline. We start with the IoT ID20 on NSL-KDD dataset, random true data preprocessing, then statistical feature scoring using ANOVA, Pearson correlation, and also chi-square. This produces a sorted, normalized feature importance curve. That curve then goes through two competing thresholding mechanisms. The first one is a fixed threshold at K15 and our proposed adaptive needle threshold at sensitivity S5. The selected features are used to train decision tree, random forest, XGBoost, and also naive Bayes models, which we then evaluate on both performance metrics and also the lightweightness metrics. For the dataset, we use two publicly sourced Kaggle datasets. The NSL-KDD is our foundation network dataset with 41 features, around 148,000 of total samples. And also the IoT ID20 mimics the modern IoT network complexity and also zero-day attacks with 86 features and around 626,000 samples. Our pipeline enforces strict isolation. The pre-processing pipeline begins with the 80-20 train test split, partitioning the data first to completely prevent data leakage. For pre-processing, we drop the high cardinality network identifier, map target classes into binary classification, where 0 is for normal traffic and 1 for anomaly traffic, and also applied label encoding for categorical handling, median imputation for missing data, and also min-max feature scaling into a normalized 0-1 range. For the feature scoring, we use three statistical features. Chi-square evaluates variable independence against the target labels. Pearson correlation computes the linear feature target dependencies. And the ANOVA F-test measures the ratio of between group to within group variances. For thresholding, we compare two mechanisms. The fixed threshold is our control, a hard-coded selection of exactly the top 15 features. And the adaptive threshold is our proposed method using the needle algorithm via the NEAT library. The needle principle locates the mathematical region of maximum curvature, the elbow point on the descending importance curve. Sensitivity was locked at a stable baseline of S5 across every run to keep the comparison fair. For the classification model, our primary classifier is decision tree, chosen for its resources efficiency, low computational overhead, and excellent interpretability on edge hardware. The pipeline was also cross-evaluated using random forest, XGBoost, and also knife bias. For evaluation, we look at three angles: detection accuracy, with accuracy, F1 score, and false positive rate. And the second one is robustness, with the standard deviation of those metrics calculated across network topologies. And the third one is the lightweightness, with training time, model size, inference latency, and memory footprint, verified using the Wilcoxon sign rank test across 20 stratified folds. Now, let us move to the results. The first result shows that what the needle algorithm actually found when we ran it across the both datasets. On NSL-KDD, needle adapted upward, selecting K15 for chi-square and K16 for ANOVA, and also K23 for Pearson to preserve the more complex decision boundaries in that data. And on the other hand, on IoT ID20, the importance curve dropped sharply near the top feature, so needle trimmed the feature count down to K10 for chi-square and ANOVA, and also K11 for Pearson. And this is really the proof point of the paper. One dataset needed more features, and the other one needed more fewer, and needle detected that automatically. The next one. So how did the actual classifier perform using those features? On IoT ID20, the decision tree came out on top with 99.94 accuracy, 99.97 F1 score, and also a false positive rate of just 0.53. Random forest and XGBoost followed closely, both about 99.8%. While knife bias lags significantly at 78.40% of accuracy and 12.81 false positive rate. On NSL-KDD, XGBoost led with 98.55 accuracy, followed by random forest at 98.52% and decision tree at 98.21%, all within about half a percentage point of each other. Knife bias again trailed at 0.75%. The key takeaway, our lightweight decision tree is genuinely competitive with heavier ensemble methods, and it's the one that's actually deployable on constrained edge hardware. So for the next table is a direct comparison between the fixed and also the adaptive thresholding with statistical significance testing. Then this is the heart of our result. On NSL-KDD with chi-square, fixed and adaptive landed on the same K15. So accuracy stayed identical at 96.94%. That is expected, as it shows our method adapts only when the data actually calls for it. With ANOVA going from fixed 15 to adaptive K16, raised accuracy from 96.93 to 98.76, and cut the false positive rate from 2.58% down to 1.10. With Pearson expanding from K15 to K23, push accuracy from 96.93% up to 98.92% and drop the false positive rate from 2.58 down to just 1.1, roughly a 60% of reduction. Both improvements were statistically significant with p less than 0.05 on the Wilcoxon sign rank test. On IoT ID20, needle went for the other direction. For chi-square, K dropped from 15 to 10, and accuracy stayed statistically flat at 99.94% while cutting 33% of the features and 37% of the training time. For Pearson, K dropped from 15 to 11, and accuracy actually improved slightly from 99.95 to 99.94 to 99.95, with the FBR falling from 0.63 4 to 0.50. So the pattern is consistent here where the data needs more feature, needles gives you more, and accuracy goes up. When it needs fewer, needle trims it and you get a lighter, faster model. And the next one, this last result slide answers our third objective directly. Thus, adaptive thresholding actually makes the model much more robust across different network environments. We measured this as the standard deviation of accuracy, F1 score, and false positive rate across NSLKDD and IoT-ID20. With chi-square, since the threshold barely changed, robustness stayed roughly the same at 2.12. But with ANOVA, standard deviation in accuracy dropped from 2.13 down to 0.84%, a 60.6 reduction. And with Pearson, it dropped even further from 2.13% to just 0.73%, a 75% reduction in variance. False positive rate variance improved as well, down to 0.41% for ANOVA and 0.36 for Pearson. In plain terms, adaptive thresholding doesn't just improve accuracy on individual datasets. It makes the entire pipeline far more predictable when underlying network topology changes. And to bring this together, adaptive thresholding outperforms a fixed K15 baseline. Our best gains were on NSLKDD with Pearson, where the accuracy improved from 96.93 to 98.92, and false positive rate dropped from 2.58 to 1.1, while matching the baseline on chi-square and on IoT-ID20. The pipeline eh, is also more robust across dataset. Cross dataset standard deviation dropped by around 75%, and the selected feature subset generalized well across classifier. Decision tree stayed best on IoT ID20 with random forest and XGBoost only slightly ahead on NSLKDD. So our key takeaway, needle thresholding proves to be a lightweight and adaptive alternative to static feature selection. Two limitations are worth noting. Model convergence still depends on the sensitive parameter at 5, which risks early underselection on highly skewed traffic data, and memory profiling metrics are frequently bound by OS level memory page resolutions, typically at 4 KB, causing zero readings for lightweight classifier. For future work, we plan to transition to true sub-process level profiling to fully isolate memory footprints and to deploy the adaptive pipeline directly onto physical edge devices and microcontrollers to empirically measure live inference latency and real-world energy consumptions. And here are some of the references that we use for the paper. This concludes our presentation. I would like to thank the session chair, our reviewers, and the ICISS 2026 committee for the opportunity to share this work. And thank you all for your attention. I'd be happy to take any questions. Thank you.